Hi all, I'm Joël Lindegger. I'm a first-year PhD student in the Safari research group, and I will show to you some of our recent work in accelerating genomics, in particular using GPUs to accelerate the GNASM algorithm. So let's start with some background on genome sequencing and analysis. So genome sequencing enables us to determine the order of DNA sequence in an organism's genome. So this genome is a set of chromosomes. Humans have 23 pairs of such molecules, and each of these is a long string of ACGT characters twisted in a double helix. And these DNA molecules, they capture a majority of the hereditary information that an organism carries. For example, in humans, eye color or susceptibility to certain illnesses, or how well someone would react to a medication. So it plays a pivotal role in analyzing this genome. It plays a pivotal role in personalized medicine, outbreak tracing, and understanding of evolution. Now there's some challenges here, because if you want to computationally analyze such a genome, you have to take some kind of physical sample and get a digital version of it. For that, you need a sequencing machine, and these sequencing machines take none of these take a long DNA as input and give the entire thing in one piece as an output. So what they do instead is all sequencing machines get small randomized fragments of this genome as an output. This poses some computational challenges, which we target in bioinformatics. So let's quickly look at the full pipeline. So we start with some kind of sample collection from a human. This could be, let's say, some blood that we get from a human. It's followed up by some preparation steps. So we, it's just like chemistry, where DNA fragments will be chopped up and potentially modified, but these are still molecules that are sent around. And so we put this in a sequencing machine, and out we get sequenced reads. Now, these sequenced reads are a digital version of the chopped DNA fragments, and so when we talk about reads, we really mean a string of ACGT characters. Or characters we call base pairs, and the entire string is a read. We then run a genome sequence analysis step, so this is purely computational over this digital data, and we run this computational analysis step on top of it. This is what in the end gives us all the output we're desiring. Now let's briefly look at these machines, because these really affect what we need to do in the downstream stage here. So these sequencing machines, there's a bunch of technologies, and some of the most popular ones are, for example, ONT, PacBio, or Illumina. And these have different properties, because some of them are more accurate, some of them are faster, cheaper, whatever. But the most important thing for now is that it's really the cost reduction that these technologies have brought us in the last years. So let's say if in 2001 the computational capability was in line with the amount of the cost and throughput of sequencing machines, then this kind of stayed in line with Moore's law until 2007, but then you saw a significant drop in sequencing cost and hence also throughput of sequencing machines, or let's say total throughput in the world. So what you see here is that really we can now sequence much more gene data and do it much more cheaply than Moore's law has scaled. So we don't have, let's say, the raw computational power hasn't improved as much as the data. So what we need to do now is have smarter, more intelligent architectures. So we use our transistors in a better way, or we could also have the same architectures but with better programs, so optimizing CPU and GPU code. But anyway, the entire point here is now that computation is a bottleneck these days, and we need to be smart about how to deal with all this data. So with that out of the way, let's briefly look how these computational steps look. We get these reads from the sequencing machine, and we do read mapping, most typically for medical applications, for example. So we have some kind of reference genome. We know that a human genome looks in a certain way. So we have one full sequence of a human genome, and we get these chopped fragments of that similar genome that we just sequenced, and we try to find what's the best locations where each of those fragments can fit. So this process is called mapping, finding the best location of a fragment relative to a reference genome. Alternatively to this, you could also do de novo assembly, where there's no reference genome and we find an assembled version just based on overlaps between these reads. So this is computationally much more expensive because you don't have this extra information from the reference genome. And that's why we will for now focus on the read mapping, which is the more standard thing to do because it's at least somewhat cheaper. When we do genome sequence analysis for read mapping, this will be always the first step for some medical applications. And as I said, we align reads to one or more possible locations within the reference genome. And our goal is to find matches and difference between the read and reference genome at that location. So how we do this alignment, or how we find this best location, is we do approximate string matching. And what approximate string matching allows us to do, as opposed to exact string matching, is to account for sequencing errors and genetic variations. So I mentioned earlier that the machines I showed, they are not always 100% accurate. They make some mistakes. It varies between technologies. Some of them are like 0.05% errors. Some of them have up to like 5 or 10% errors. So if you have errors in your strings, you cannot do exact sequence search. Instead, you have to do an approximate search where you allow some kind of errors, and still you want to find the location that has at least the fewest number of errors. And then there can be, of course, genetic variations in the same line, but here it's not the machine that does the mistake, but rather that our reference genome that we map to is genetically different than the human that we sequenced, whose DNA we sequenced. Now, these steps are bottlenecked by the computational power and memory bandwidth of existing systems. And this is the point where this approximate string matching is really one of the main bottlenecks, and that's what we also are trying to accelerate. But that's this introduction I want to give on genomics. You can find more on our PNS genomics courses. There's a lot of great materials in there. But for now, let's focus on this approximate string matching. So in approximate string matching, we have a sequenced genome that may not exactly map, as we said, due to these variations and sequencing errors. So let's say we have a reference in the read, and you can kind of see they already look somewhat similar, but actually there is a deletion in here. So a character that appears in the reference but was missing in the read. There can be substitutions in here, so characters that occur but are actually different in the read. This could be a genetic variation or a mistake by the sequencing machine, or an insertion, a character that for whatever reason occurred in the read but actually wasn't in the reference. And now approximate string matching tries to account for all of these. It tries to find the differences and also similarities between the two sequences. And we've used this to find the minimum edit distance. So a minimum edit distance is kind of our optimization target. We try to find whatever mapping location and edit sequence has the fewest total number of edits in there. And in addition to the fewest number of edits, we also want the optimal alignment. So this is really the exact sequence of edits here. So the first thing is the optimal number of edits, and here is also the exact sequence of edits. We usually compute this using dynamic programming algorithms. So this might be one that you have seen in some introductory algorithms course at ETH. I think at least computer science students should have seen this one, as called Wagner-Fisher or Smith-Waterman algorithm. And what we have here is, let's say you have the reference sequence and the read, and we build a two-dimensional table. So this is one of the most common algorithms used for this, and has quadratic space and time complexity, because clearly you're filling a quadratic table of numbers. Now, alternatively to this number-based, arithmetic-based dynamic programming, you can do bit vector-based dynamic programming, and this is called the BiTAP algorithm, this example. So you build, there's still a table that's still two-dimensional with different axes than before, and entries are bit vectors instead of numbers. So really, each of these bits we are considering as Boolean values and not as numbers. So this will be the algorithm that we will try to optimize later on GPU. So let's quickly look at some pseudocode here. So it consists of a two-dimensional loop, of course, because we fill a two-dimensional table, and the actual computation is all bitwise operations. So this is really the motivation for doing this, as opposed to the arithmetic dynamic programming. Bitwise operations can be much more efficient, and especially implemented in hardware. And depending on the architecture, this might also have, for example, lower latency to execute or higher throughput. And then, of course, there's some kind of output calculation. And notably, in this case, actually, the output is only the number of errors. So this algorithm, as it stands here right now, can only determine the optimum number of errors. But as we discussed, actually, we need traceback for the genomic workload. So if you have only the optimal number of errors, this really corresponds to, let's say, the optimal cell in this kind of table layout. And the optimal sequence of edits is a path in reverse. So this optimal sequence of edits can be determined by following Traceback, a Traceback algorithm, which tries to find where at each step along the way the partial optimal solution was. And if you concatenate these partial optimal solutions, that's your optimal sequence of edits. And we also call this the cigar string in genomics. Now, the BiTAP algorithm that I showed didn't originally, at least, come with this support for this traceback step. So here we come to this Genome work of, led by my master thesis advisor, Damla. And so they proposed Genome, and among other things, so they hardware accelerated BiTAP, but they also algorithmically extended the BiTAP algorithm so that it has traceback, and they did some kind of performance improvement. So that the windowing heuristic and some, they showed that there's actually parallelism in this algorithm. Let's not get into these, but let's quickly look at this traceback thing, which is a necessity for us. So this was the algorithm that we had, and what Damla et al. Figured out in their work back in Micro 2020, they figured out that you can just store these intermediate bit vectors. So all of these across all two iterations of the two loops, and you follow a trail of zeros in stored bit vectors in reverse, and this will be the optimal sequence of edits. So now we have a full algorithm, and they showed in this work kind of that, this works really nicely in hardware, it's highly efficient, and they showed that this has also some parallelism. And of course, at this point, we were motivated also. If you have parallelism and it's already quite efficient, it kind of makes sense to try and implement this on GPUs and see how it works. So first implementation attempt for this algorithm could be to take this existing C code with CUDA, have some minor changes in it, just take the CPU code and recompile it. And then, of course, you have one GPU thread per sequence pair if you are no more specific than just taking CPU code. And we used global memory at first. So we don't have to worry too much about capacity issues or anything like that. And well, this immediately leads to actually suboptimal performance. So if we look at a roofline model, this is of an NVIDIA A6000 GPU, this is a Ampere, so the most recent architecture of NVIDIA. It's a very big GPU, and this is the roofline model. So you have the bandwidth of global and shared memory and peak compute throughput. And if we store the DB table in global memory, as we did here, we actually notice in this roofline model that we would be severely memory bound. So we drew the operational intensity of the GNASM algorithm, and at the intersection point, we see this is the maximum attainable throughput that you could ever get. And it's far from what the peak throughput could be, the computational throughput could be of the GPU. So we don't really like that for a computational problem. We would prefer to be somewhere close up to here, at least in terms of peak performance. But due to the global memory bandwidth, we will be limited to this kind of performance. So as a second implementation attempt, we could try to keep everything the same, but replace the global memory with shared memory. So that's where we put the DB table. And indeed, right, this has a much higher bandwidth, because it's on chip and very close to the actual functional units of the SM. And now indeed we can be compute bound, at least in theory, according to this roofline model. But as you know, this shared memory actually has much lower capacity compared to global memory. In this context, we maybe should look at how much this will be an issue for us here. So this was what the Traceback algorithm does, right? It stores all these bit vectors, and afterwards has to use them to trace back through. And then we can quickly calculate the memory footprint over this. So let's see, we have certainly the bit vector size, the size of each of these bit vectors. This happens to be as many bits as the pattern string is long. Then we need to store 3 out of these 4 bit vectors because, well, one of these is just the shifted version of the other, so 3 of them are sufficient. And then we have the loops, so the outer loop and inner loop. So this K, by the way, is a edit distance threshold, the maximum number of edits considered. So what's crucial here is that this is several terms multiplied together, and let's say we assume text and pattern lengths of 64 and a single warp of 32 threads. And recall that one thread works on 1 copy of this data. We get a footprint of 64 times 64 times 3 times 64 bits, so this from the previous formula, times the 32 copies for each thread. And this is like 69 kilobytes times 32, 3 megabytes. This is a lot. The shared memory capacity of the Ampere SMs is 99 kilobytes. So per SM you can have 99 kilobytes of memory, but actually our algorithm as we implemented it right now needs 3 megabytes. So clearly this implementation would fail because simply we are out of shared memory. Either at compile time or at runtime you would get an error. So for our third implementation attempt, we can try to rewrite the code for GPUs specifically, and try to rewrite it such that it's a thread cooperative manner. So you can have, let's say, 64 threads in a thread block and have them cooperate on a single sequence pair. Then still we store the DB table in shared memory, and hopefully we can that way actually now attain this compute bound case. So how do we map these threads to cells? Clearly we need some kind of parallelism if they want to cooperate. So this is the table that we're trying to calculate, and indeed it turns out, so they figured this out in the GNASM work, in the original one, that you can map threads to columns in the table. And then there needs to be some communication between these threads afterwards, but at least you can somehow work on these columns in parallel. So yeah, by the way, that's why I said there's 64 threads here. We can have one thread per column, and if you assume text and pattern are again 64, we can use 64 threads. Okay, we use 64 threads in one thread block, and this gives us a footprint of this formula as before, times 1, because they all cooperate, is 96 kilobytes. And indeed, as we had before, this fits into the 99 kilobytes of shared memory in the Ampere SM. So this is nice. We at least got it to run for now. But now we get into some performance issue. So as I showed, this fits barely one instance, right? We can fit one thread block of 64 threads. At least it can only be active at any given time. You can only have one active thread block in the SM because, well, you can fit only 69 kilobytes once into 99. And having only one thread block in an SM, if the thread block is only 64 threads, it's really not enough to saturate the SM. So we call this low occupancy, and this is bad. Occupancy should be high for good performance, such that the simultaneous multi-threading and GPUs can hide instruction latencies. But for the simultaneous multi-threading to work, we need many active warps, and clearly this would be only 2 active warps of 32 threads. That doesn't give us sufficient latency hiding for good performance. If you want to get more background on this kind of occupancy issues and why it's exactly needed and how this SMT works here, you can refer to our previous lecture. So Juan presented here many performance considerations, including these occupancy issues. But for now, let's set away this attempt and say, okay, it will have low performance simply due to this low occupancy. It works, but we were kind of limited due to the memory capacity, right? If our memory capacity was much lower, this would have been great. We could have fit maybe more thread blocks, but as it was, we could only fit a single one, and that gave us bad performance. So at this point, we can get to our recent work, Scrooge. And what we did in Scrooge is algorithmically improve the Genome algorithm, and of course then as part of it we did a GPU acceleration also. We present this in HiCom just this May. It's a workshop in genomics, and it's a short paper is currently available on arXiv. You can see the link down below here. So let's quickly look at an executive summary here. We went over the motivation here. We need fast pairwise sequence alignment, and Genome is this kind of highly efficient state-of-the-art algorithm. It was really good also in hardware, and it has some parallelism in there. We're motivated to explore it on GPUs. And we observed that there are some inefficiencies in there, and in particular for now we should look at this memory footprint issue, right? For right now we're fighting the occupancy problem on the GPU, so we're mostly interested in this large memory footprint problem. So our goal was to get these fast and efficient implementations for a variety of platforms, and what we actually figured out is that we can get some algorithmic improvements for the Genome algorithm. So the mostly relevant ones here are Sene and Dent, which address the memory footprint issue and also reduce the data movement. And we're actually able to show that this gives quite significant speedups, just these algorithmic improvements, especially on GPU. So let's look at why this was. Why do we get such high speedups, almost 6x? So we figured out that in the DP table, the original Genome algorithm stores 3 edges. Right? In the pseudocode I showed, these were bit vectors. If you draw it as a table layout, these are really these arrows or edges between cells. And it stores 3 of these per cell. And what we figured out is that it's actually sufficient to just store the cells themselves. And when we need the edges during traceback, we can just regenerate the arrows that we need during that time. And since this one is only 1 bit vector per cell instead of 3 bit vectors per cell, this gives us immediately a 3x reduction in memory footprint and data movement. That's our first improvement. We call this Sene store entries on the edges. Now for our second improvement, we observed that certain areas in the DP table are actually never reached by the traceback step. So this is related to one of the performance improvements in the GNASM algorithm, the windowing heuristic. I will refer to the original GNASM paper on how that exactly works. But the point here is that the traceback step in this table never reaches the right half of each bit vector, and it never reaches the right half of the table. So what we can do is at runtime simply never store these. We do need to calculate these areas, but we never need to store them for traceback. And this immediately gives a 4x reduction in memory footprint and data movement. So with these two improvements, Sene and Dent, we can get to our fourth implementation attempt, which I will call Scrooge. And we again have threads that cooperate in a thread block, use shared memory, and now we also algorithmically reduce the memory footprint. Right? We had these two improvements that improved by 3x and 4x respectively. And together actually they combine very well, and you get a 12x total reduction in memory footprint and data movement. So this is really nice. Now let's check the memory footprint again of this implementation. Let's assume again text and pattern are 64 characters long. You get 12 thread blocks. So notice I already scaled up the thread blocks because we have a 12x reduced memory footprint, and we can use 12x more thread blocks. So the calculation kind of works out. We save half of the table, half of the bit vectors, and we only store 1 bit vector per entry. And well, this allows us then to use 12 thread blocks instead of only a single one, because for each single thread block, the memory footprint is only 8 kilobytes, and these 96 kilobyte total fit into the shared memory capacity of an A6000 GPU. So this is really good because these 12 thread blocks are enough to what we could call high occupancy. This gives us high performance actually, much higher than what we had without these algorithmic improvements. So I can show you some proof for this. This is not all hypothetical. So here we have in green we have the full algorithm with all our improvements. That is Sene and Dent, and actually some third optimization which does some reduces the computational workload. But mainly what the speed up we get here is occupancy, because these Dent and Sene only implementations have lower occupancy. They also get significantly lower performance, and you should really have a forced line here that says GNASM without either Sene or Dent. But unfortunately, you cannot run it in practice with our implementation because our implementation uses slightly more than 96 kilobytes of memory, so you can just barely not fit it into SRAM, into shared memory at all, even with a single thread block per SM. So if you could run it though, it would the bare bones GNASM would only scale to 1 thread block per SM, which would be a line like down here, as that's basically where these lines start out. So really the gap from down here or down here to up here is the increased occupancy. So yeah, this I guess all these steps together, right? We have our cooperative with many threads in a single thread block, plus actually multiple algorithmic changes, and together we get kind of decent performance on a GPU. Okay, so that's this aspect of it, and now I actually also want to show some really nice, let's say, low-level implementation considerations that we made. So as one of the pre-processing steps in the GNASM algorithm, we need to generate pattern bitmasks. What we have to do is we come from an ASCII encoding of the data, and we have to go to some kind of one hot or one cold encoding of the pattern string. So a one hot or one cold encoding in this case is you have 4 bit vectors, a bit vector for the character A, a bit vector for the character C, G, and T, and so on. And they have a 0 in the respective bit vector if there's that character at the given location. So the last character here is an A in the pattern, thus the last bit in the A bit mask is a 0. Similarly, let's say here for the C character, the C bit mask has the first bit 0 because, well, there's a C as the first character in the pattern. Now the challenge here is how do you efficiently compute these bit masks? What you certainly could do is some kind of serial implementation. So you first initialize all bits to ones, then you go over every character in the pattern, and for each character set the appropriate 0 in one of these bit masks to a 0. So this kind of works, but it's really bad because there's no parallelism. So only one thread block would do all the useful work in the only one thread in the thread block would do useful work, and all the other threads either do redundant work or no work at all. This is bad, right? So what we realized is that one of the most standard patterns in GPU computing can be applied here. It's parallel reductions. So what we can do instead is to initialize the bit vectors to all ones, and then have each thread have its. So these are local copies of the bit masks, really, and then you have each thread set in its own bit mask only a single 0. So at this stage, each thread has a set of bit masks with only a single 0 in it. And then you can merge all these bit masks together with a parallel reduction. So you can either manually implement this parallel reduction using such a loop. So it would be backwards compatible to older GPUs. And in more recent GPUs, there are actually even specialized instructions that can do this. So you have one instruction that does this kind of bitwise AND over all threads. Now this is much better because you have a large amount of parallelism. Every thread in the block does useful work, and mainly the speed up you get is that this loop here is much shorter than the loop that we had before. Before the loop ran over the entire pattern, and here it's a kind of a logarithmic length loop. So you can find out more about parallel reductions in this parallel patterns lecture by Juan from this earlier lecture in the PNS course. So this was one of those considerations we made, and another nice one is how to resolve data dependencies. So if you recall, we had we have many threads cooperate on calculating this DP table, and we mapped the threads such that one column is calculated using a single thread, the next column is calculated using a different thread, and so on. And inherently from the algorithm, you get some data dependencies. So you get top-down and right-to-left data dependencies. This has nothing to do with the GPU implementation, but it's simply inherently in the DB table, that's the order you need to calculate it. Now there are two kinds of data dependencies in here, right? There's the vertical ones, which stay within a thread, and there are ones that cross across threads from right to left. This order of calculation. In the first iteration, you can only calculate this entry, and then from the data dependencies in the next iteration, you can calculate these two. In the third iteration, you can calculate these, and so on. And now the question is, how do we actually resolve the data dependencies? So yes, we show we can do it in this order, but how do we actually communicate the data? What's the actual mechanism to communicate the data between threads? So what we can do is do memory access all the time, but this is kind of undesirable because then we need to have every thread write to memory every time and read back from memory, and as kind of high latency, high bandwidth. It's really not optimal in any way. So register accesses would really be preferred, and this works trivially if the data stays within your own lane, right? So a GPU thread can access its own register without any problem. But where it gets challenging is these inter-thread dependencies. So we somehow need to move this data over here to the next neighbor thread for the next iteration. Can we do that using registers? And it turns out, yes, if you followed this lecture series. So there are these warp shuffle instructions in CUDA. So a screenshot from the CUDA programming guide. these intrinsic shuffle sync, shuffle up sync, shuffle down sync, shuffle XOR. In our case, shuffle down sync, I guess, is what we needed. So we shuffle values down by 1. Right? So down means from a higher thread index to a lower thread index. And yeah, this shuffle instruction can do exactly this. So by its description, it permits exchanging a variable between threads of a warp without the use of shared memory. So this is exactly what we need. And then, yes, we might note here that it says only within a warp. So to do the remaining communication across warps, because we have a thread block of more than one warp, we actually still do need some memory accesses, but it's at least not as much as before. Yeah, if you want to find out more about these warp shuffle instructions, you can check out this parallel lecture by Juan. Again, this parallel patterns lecture, it's a really nice lecture. And let me conclude with some numbers here. So in an early stage of the project, we got to some throughput number of 1,800 alignments per second on some configuration of our data set and GPU. And by the end of the project, we were at something like 25,000 alignments per second. So this is like over 10x improvement in throughput. And we applied all these techniques that I showed. So among them, using shared memory, using a thread cooperative implementation, algorithmic improvements to reduce the memory footprint and get higher occupancy. We use parallel reductions to efficiently calculate bitmasks. We use warp shuffle instructions to resolve data dependencies. And in my own conclusion, this really ends up being that optimizing GPU code requires a holistic view of the program. So ignoring any of the above aspects would ruin the performance of the program. So if you were to go through our source code and remove any of these, it kind of breaks the performance. That's that about this project. If you want to check out some of our other PNS courses, especially bioinformatics, if you are interested in that, we have it on our website with many video lectures. And there's of course all of Professor Mutlu's lectures, also from computer architecture and advanced computer architecture. So thanks for your time, and hope to see you again. Bye bye.